This video is sort of an addendum or a fill in the blank for the video lecture from this morning on May 28th, 2020. So basically, for about 30 minutes or so, I had OBS set to the wrong output scene. So from about 17 minutes in the video to about 47 minutes in the video, it was showing the wrong screen, and that's just me making a mistake. Basically, I have a lot of windows, and I have two monitors, which is pretty good, but somehow it's still not enough space. And so if I'm watching the YouTube stream quality, I have to have that in front of OBS, and so I can't see OBS. And if I have OBS in front, I can't see the stream quality. Um, yeah. Anyway, I might have to try to figure out a different setup here so I can be a little more effective in that regard. Anyway, so what I'm going to do is I went and made a duplicate of the 2 pages of lecture notes from that time period, the 30 minutes. And I went through and I erased all the results. I just kept the setup of every example. So we're going to go through these and I'll basically work through the problems. It shouldn't take 30 minutes probably because there was some back and forth question and answer during that time. So this will be probably like 20 minutes, most likely. We're already at just over 1 minute. So the whole video is going to be under 25, I think. Maybe it'll be like 21, 22, something like that. Anyway, so we talked about doing limits numerically, right? Like this example here, we made a table, we picked numbers, and we chose X inputs to get closer and closer to 2. And we looked at, well, what are the outputs doing? What are they getting closer and closer to? In this case, we got 4. And then we looked at doing things graphically, where you have a graph, and you just look at it. Oh, yeah, that sure looks like when you follow the graph down to X going to 1 from the right, the Y coordinate goes to 1 from I think we decided from below, because we decided that the graph dipped down and came up again, is what I recall. Anyway, so now what I want to do is do something that's called a more analytical approach. So we're not going to pick specific numbers necessarily. I might refer to them as well, just to transition into using an analysis rather than a numerical approach. And then not having a graph. Now I will draw the graph afterward, but I want to work this out first. Okay. So here's my function: f of x equals 1 over x. So the output is just the reciprocal of the input. And I want to look at these two limits. The left limit and the right limit as x goes to 0. So of course we could make a table, but I want to do a different approach because doing a table is tedious and you don't really need to do it that way. Doing a table is basically a way to get the concepts. You understand what a limit is. And then this is the more useful approach to solving this kind of problem. So if if x is approaching 0 from the left, then x is always negative, right? Because x doesn't equal 0, it's just going to 0. It's very, very, very close to 0. Now, that means since x is negative, that this whole fraction, 1 over x, is also negative. Negative. 1 divided by a negative number will be some negative number also, right? And x is very, very small. It's very, very close to 0. So if I were doing a table, I could pick like -1, -0.5, -0.1, -0.01, and then plug those in, get my reciprocals, and see what I get, right? And I could, maybe conclude some pattern based upon that. But I don't want to do it with a numerical table. What I want to do is this. Basically, since you can't divide by 0, like if we were to plug in 0, we'd have 1 over 0, but you can't do that. That's not defined, right? We talked about that last time. So that means that there's an asymptote, most likely, right? I don't want to say guaranteed, but let's say most likely. If you have a non-zero number divided by 0 by plugging in something, that means you have an asymptote. I don't want to say certainly, but at least in this case we do. There might be exceptions. So if we have x getting closer to 0, that means the bottom is shrinking. Now, if you have a fraction, let's say I have like 8 over, say, 2, right? That's equal to 4. And of course, I don't mean equal to that. I'm just putting it next to it. Let's do this. Okay. Now, if I were to increase the bottom to 20, the denominator to 20, oh, now the whole fraction is smaller, right? If you increase the bottom, the whole fraction shrinks. If you increase the top, of course, the whole fraction grows. Now this is 40 rather than just 4. Similarly, if you decrease the bottom, this is now larger. This is equal to 40, because it's basically 80 over 2. 8 over 0.2 is the same as 80 over 2. So I've made the fraction larger by shrinking the bottom. And if I shrink the bottom further, right, now this is 400. I've made it even larger as a whole. The fraction is larger. So if my denominator goes to 0, then the fraction itself will grow without any limitation. It'll grow to infinity, essentially. So our limit is infinity in this case. However, we're approaching from the left, so we have negative infinity. Okay, 1 divided by some really teeny tiny negative number will be a very, very large negative number. And if we shrink the bottom to 0, the fraction as a whole grows to infinity, but again, negative. On the other side, if we are approaching 0 from the right, or if x is approaching 0 from the right, we have a similar thing. There's just no negative involved. The bottom shrinks to 0, so the whole fraction grows to infinity. Okay. So this basically tells me that in the graph, when you approach the vertical asymptote from the left, the graph curves down, and when you approach the vertical asymptote from the right, the graph curves up. That's basically what that says. So over here, these coordinate axes, I can draw that. Now, you might already know what this graph looks like, or not. And you can use basically the limit information to inform how to graph it. So I already know what it looks like, so I'm just going to graph it the way I think it should look, and then I'll refer to the limits after that. Okay, so when you follow the graph, let's change colors here. When you follow the graph from the left, right, the graph goes down to negative infinity, curves down. When you follow the graph from the right with x going to 0, okay, the graph, the graph goes up, okay, to positive infinity. Okay, so that's essentially what the limits are telling me. The one-side limits when you have an asymptote are telling me, well, which side goes up, which side goes down, is essentially what that's telling me. Okay. This is called an odd function because it has symmetry across the origin. This is something you might remember from pre-cal. If I take this point right here and I reflect it across, there's another point on the graph that corresponds to it, and every point is like this. Each point has a partner on the other side of the origin. So I could do this point here, and this other point is equal. If you draw it well, it's equidistant, right? So that's called odd symmetry. Or this is called an odd function. That's a bit of a side note, but it's something that we will want to consider from time to time. Okay, so how about this guy? How about this function? 1 over x squared. It's kind of similar, but I'm squaring the bottom. And in the virtual lecture, I asked, okay, guys, what do you think? And someone relatively quickly said, oh, well, this is going to be positive infinity. Let me change colors here. I said, that's right, but how do we know? Why is positive infinity? I'm sorry, that I didn't say why yet. At this point, someone said, oh, okay, it's infinity. I said, okay, why are they both infinity? That's what I had said. And the reason is that although on this right-hand side, this one over here on the right, when x is going to 0 from the left, x is always negative, but you're squaring x, so it being negative doesn't really matter. So because we're squaring in the denominator, both limits are positive infinity. They're both infinite in size for the same reasons that this one was, because the bottom's shrinking to 0. But since we're squaring the bottom, there's no negative result. Okay, let me do a little bit here. Okay, so since these two agree, they're both infinity, both positive infinity, that means the two-side limit is infinity as well. Whereas in this the previous example, there was a disagreement. So up here, actually, I could say, oh, the two-sided limit as x goes to 0, 1 over x does not exist, d and e, because the two one-side limits are different. The graph diverges. One side goes up, one side goes down at the line x equals 0. The vertical line x equals, the vertical line x equals 0, which is also the y-axis. So here, I get agreement. So if I graph this one, it's going to look a little bit like this. As you follow the graph on the left, or rather from the left, you follow the graph up, right? You're going up to positive infinity. And when you come from the right, you go x goes to 0 from the right, you follow the graph. Well, you're also going to positive infinity. They agree. They both go to the same place, so we get a two-side limit. The two-side limit is infinity. Some books won't do this, especially older books. They'll say something like a two-sided limit must be a number or it does not exist, that you can't have infinity as a two-sided limit. Um, the textbook we're using doesn't do that, and I typically don't do that anyway. I think this is totally fine. You're describing what the graph is doing. When the two-sided limit exists, the both sides of the asymptote, both the two components of the graph on either side of the asymptote both approach the same direction when you x moves towards the asymptote. Okay, so next example is just a variation on that, a little bit harder, a little bit more detail. So for this one, you can't always tell just by looking at it. The limit as x goes to 4 of 1 over x minus 4 to the fifth power. This is a little bit more involved because of the 4 and the 5, right? We have a bigger exponent, and we also have subtraction in those parentheses. So this is a little bit more complicated. Now, there's several ways to do this. The way I'm going to show you to do this is basically I'm going to be justifying why I have this result. After you've done this for a while, you can just kind of look at it and go, yeah, I see what's going to happen. I know the answer. You can draw a conclusion without really writing anything. But of course, I'm going to justify this so that you're seeing this for the first time. It needs to be clear, and also I'm going to show you this is how you justify your result. And there's more than one way, but I'm going to show you one way, and then I'll talk about another way. So if I'm coming at -4 from the left, that means that x is less than 4, right? It doesn't have to be negative. Like if I were picking numbers, if I were doing a numerical table, I was picking numbers, I would go x is 3, x is 3.5, x is 3.9, x is 3.99, right? But those are all less than 4. So I'm going to write that here as an inequality, x is less than 4. Now, in the denominator, I don't have just x. I have x minus 4. So I want to know, well, what is x minus 4 like? Is it positive? Is it negative? Is it going to 0? Right? If x is going to 4, then x minus 4 would go to 0. Like if x becomes 4, then of course x minus 4 is 0, right? But again, the limit, when we're considering the limit, we're not saying, oh, x is 4. We're saying, well, x is really close to 4. What's the behavior of the graph when x is really close to 4? So I need to manipulate this inequality to see what x minus 4 would be like. So if I subtract 4 on both sides, I'll get x minus 4 is less than 0. It's negative. So this inside part is negative, right? And it's going to 0, right? So that means I have an asymptote, and the denominator is negative. Well, the x minus 4 is negative, and then I have a fifth power. And when you raise a negative number to a fifth power, you still have a negative, because you'll have a negative number times a negative number times a negative number times a negative number times a negative number. You have an odd collection of negative numbers, so the total is negative. So that tells me negative infinity. And the justification is this inequality. If like on a written homework or an exam, you could say, oh, this is negative. And then say, oh, this maintains, or let's say keeps, simpler word, keeps negative, right? Yeah, that's the reasoning. This is more clear. You're being very explicit on what's happening. But this reasoning is, this is an appropriate way to reason through it. So on an exam, if I just say, if the problem is here, find this limit, and you just give the answer, well, you did. So most likely the test problems would say, like on the web work component of the test problems, you just got to get the answer right or wrong, right? Just hopefully right. Just get the answer right. On the written part, well, you're gonna have to justify your reasons. Why is this the answer? And I will probably say something like, here, find this limit and explain your reasoning, right? And part of the point would be, is it the answer right or not? But part of it would be, well, did you show this? And at least half the points would be, have you shown why? If you just put the answer, you're not going to get very many points, because the point of the problem is for you to show me. And this is something I said earlier this is part of the reason that the lecture ran up to 30 minutes, because I was talking about the exam. So we might hit 30 minutes here anyway. So because I don't expect you to go watch 30 minutes of video where the sound and the screen don't really match. I'm expecting you to skip that. So, if I only cared about you getting answers right or wrong, well, then I would just do the whole exam on web work. Why even have a written part? It's easier for me if I don't have to grade, right? But I want, for a number of reasons, I want to see your work. I want to see your justification, in part so I can grade it and correct it and show you, okay, this is right, this is wrong, this is how you should have done this differently. Write comments so you learn from that. A midterm exam, and not meaning just that there's one midterm equally in the middle, but throughout the semester, exams are not the final exam. Part of their use is pedagogical, that you're going to learn from the results. I write comments, you read them, and you get a better understanding. So that's why we're doing written exams rather than just on web work. Anyway, so the other side, I got similar reasoning. But now x is going to 4 from the right. So x is greater than 4. If I subtract 4 on both sides, I get x minus 4 is greater than 0. So x minus 4, this is positive, right? And then, sometimes the Zoom share, I think it's just, this app does it. Okay. Sometimes it freezes. I just have to put it away and bring it back up. Sorry about that. Anyway, as I was saying, so since x is going to, wrong button there. Since x is going to 4 from the right, x is greater than 4, and I can take that inequality and subtract 4 on both sides, because it's really x minus 4 that I care about. X minus 4 is positive, okay? Meaning that the exponent doesn't really matter at this point, because an odd exponent versus an even exponent, the result's positive anyway. If the input's positive, the output will be positive. So I have 1 divided by a positive number that's shrinking to 0, so I get positive infinity that way. Okay, so because these two one-side limits disagree, they're not the same, I don't get a two-side limit. So this two-side limit does not exist. D and E. Okay. Someone in the class asked, could you just say no limit? And you could do that. You could say no result, no limit, does not exist as the standard way. In the WebWork homework, you'll actually type D and E as your answer in that case. So one more example, and then I think that'll take us to where the video got corrected and I started showing the screen correctly again. So one more example. I have this example here. The limit as x goes to 3 of 1 over 3 minus x to the 4th power. Oops, sorry, trying not to hit the microphone there. So I want to do the two sides separately. Sometimes you can tell just from looking, and you could pause the video and think about it. Can you tell from looking what the result is? And can you articulate why? So let's go through the same process we did here, and we'll see what we get, and then I'll talk about a shortcut. So since x is going to 3 from the left, that means x is less than 3. Okay, x is less than 3. But I really care about 3 minus x. So I need to rearrange this so that I have 3 minus x. So I guess, I could subtract x on both sides of the inequality. So 0 is less than 3 minus x. So 3 minus x is positive. This guy is positive, and so the exponent of 4 maintains the positivity of the input. So I have 1 over some teeny tiny positive number. So I get positive infinity. And I should point out that the fact that I have 3 in both places, in order for you to have an asymptote, you would have to have 0 by plugging in 3 in this case. Like if I had like a 5 here, well, then the problem would be different, because you just plug in 3 and get a result that way. You wouldn't bother with a limit necessarily at that point. So the fact that they're both 3 is essential for this example to work this way. So over here, if x is going to 3 from the right, that means that x is greater than 3. Okay, so x is greater than 3. And if I really care about 3 minus x, 3 minus x, that's what I want to know about. I need to, again, subtract x on both sides. So 0 is greater than 3 minus x. So that means 3 minus x is negative. However, in this case, we have an even exponent. When you raise a negative number to an even exponent, the result, I may have misspoke. When you raise a negative number to an even exponent, the result is positive, right? Because you'll have a negative times a negative, which would be positive, and then a negative times a negative, which would also be positive. Okay, so we get infinity in this case, positive infinity. And they agree, they're the same. So that means that my two-side limit is infinity. Okay, so yeah, and that is one where you could look at the 4 and say, oh, whether the 3 minus x is negative doesn't matter, because I have an even exponent. I know the result's going to be positive. So you could skip writing all this if you notice that. So on a test, you could go through all this reasoning, and that'd be totally fine. But you could just, make a little note and say, positive. So like even root, not root, sorry. exponent. My mistake. Exponent, arrow, positive result. Right? That's the reason. So on a test, if you want to just tell me here's my answer, here's how I know, that's fine. And it's okay to use a sentence. Probably use a complete sentence, not just jotting down a note like this, but I guess I'll accept that. If I can tell what you're saying, that's fine. But try to make it clear. That's totally fine. If you're giving the reason and it's a good reason, and then of course going through these details, you might want to test, go through all those details and realize, oh man, I didn't have to write all that. Well, that's okay. You're solving the problem. That's fine. So that's pretty much it. That takes us up to where the other video got corrected. So yeah, we're done in about 20 minutes, just shy of what I thought we were going to do. So there's that. I'm going to try to clip this together with the other one. We'll see how that goes. So thanks for watching.